Right now, 230 million people are staring at what could be the largest infrastructure failure in American history. And here's the part that should terrify you. The storm causing it isn't even the most dangerous part. Winter Storm Fern has already crossed the threshold from weather event to civilizational stress test, coating the Mississippi Delta in catastrophic ice while burying New England under record snow. But what's following behind it, the Arctic blast now sweeping south, is what turns power outages into survival scenarios. Over the next hour, we're going to walk through how a storm this perfectly destructive even happens, why the models barely saw it coming, and what it reveals about systems we thought were unbreakable. Because Fern didn't just hit America, it hit something much deeper. Subscribe and follow along, because what unfolds next will determine whether Fern was a freak event or the first domino. Because when ice, snow, and Arctic cold arrive in perfect sequence to break the exact systems we depend on, that's not coincidence. That's the atmosphere finding a weakness. And once a weakness is found, it gets exploited again. You need to understand something right now. Superstorm Fern is no longer governed by prediction. It's governed by failure mechanics. I'm not talking about a weather event that's developing or approaching or threatening to become something worse. I'm talking about a catastrophe that's already unfolding across the continental United States as we speak on January 24th, 2026. And the most terrifying part? The transition from this could be bad to this is now unstoppable happened so quietly that most people are still checking their phones for updates on a storm that's already destroying infrastructure 3 states over. Sometime between midnight and dawn this morning, meteorologists stopped using the word forecast and started using the word ongoing. That's not semantic hair splitting. That's the sound of professionals realizing they're no longer warning about a future event. They're narrating a present disaster. Let me give you the numbers that made the National Weather Service go silent for a moment before issuing their latest bulletins. The Mississippi Delta, a region that sees maybe 1/10 of an inch of ice in a bad winter, is now measuring ice accumulations converging near 1 full inch. Not sleet, not freezing rain that melts on impact. Ice, actual glaze ice, building up on every surface, every power line, every tree branch, with the structural integrity of concrete and the weight to match. Meanwhile, in southern New England, something even stranger happened in the forecast models overnight. The snowfall ceiling, that nice clean upper limit that tells you expect between 12 and 18 inches, just vanished. Forecasters quietly removed it from their graphics. You know what it means when meteorologists stop giving you an upper bound? It means they're confident the number is going to be higher than they're comfortable promising. It means they've looked at the radar and the models and the real-time observations, and they've realized that putting a cap on this thing would be lying to you. The National Weather Service doesn't throw around the phrase potentially historic very often. They have an entire internal review process for that kind of language because they know the weight it carries. They know that once you say historic, you're not just describing a storm. You're describing an event that will be used as a benchmark for decades. You're saying this is the one future forecasters will compare everything else to, and they used it. For Fern, this morning. But here's what should really make your skin crawl. Those words, potentially historic, were written before the first power line fell, before the first interstate shut down, before the first county declared a state of emergency and closed its roads to all non-essential travel. The historic part hasn't even started yet. Right now, as you're reading this, somewhere in Arkansas or Tennessee or Mississippi, someone is watching their lights flicker. They're hearing that pop, pop, pop sound of tree limbs cracking under the weight of ice they were never designed to hold. They're seeing the glow of transformer explosions on the horizon, little firework bursts of green and blue that mean another neighborhood just went dark. And those people have no idea that in 12 hours, the temperature is going to drop to 10 below zero. That's not an exaggeration. That's not worst-case scenario thinking. That's the forecast. The actual, locked-in, already in motion forecast. You want to know why your weather app is suddenly useless? Because weather apps are designed for prediction, and prediction requires a stable system that follows rules. Fern stopped following rules sometime yesterday afternoon. Once infrastructure starts failing, once the cascade begins, the models can't keep up. They don't account for the feedback loop of a grid collapse. They don't factor in the compounding problem of emergency vehicles that can't reach people who need help because the roads are impassable, and the people who plow the roads can't get to their trucks because the power is out and the garage doors won't open. This is the thing about disasters that nobody tells you until you're inside one. The weather is just the ignition. The real damage comes from everything that breaks because of the weather. And right now, across a 2,000-mile stretch of the United States, from the Gulf Coast to the Canadian border, those things are starting to break. I need you to recalibrate your mental model of what a winter storm means. Fern is not a snowstorm with some ice mixed in. Fern is not a cold snap with some precipitation. Fern is an infrastructure stress cascade that happens to be triggered by atmospheric conditions. It's a system-wide test of every assumption we've made about how much abuse our power grid, our transportation network, and our emergency response capabilities can take before they stop working entirely. And here's the part that keeps me up at night. Millions of people are entering sub-zero conditions right now with no certainty that their power will stay on. Not low probability, not unlikely, no certainty. We've crossed the line from "this is concerning" to "we genuinely don't know how many people are going to be okay on the other side of this." Traditional storm coverage talks about snowfall totals and wind speeds like they're the story. They're not the story. They never were. The story is the 20-minute window you have to get your family somewhere warm after the power dies, and the temperature inside your house starts dropping 1 degree every 6 minutes. The story is the propane shortage that's coming in 3 days because the trucks can't get through. The story is the hospital running on backup generators that were designed for 6-hour outages, not 60-hour outages. You want to understand why this storm is so dangerous? It's not attacking the country with one massive punch. It's attacking from 3 incompatible angles at once, in a sequence that feels almost deliberately engineered to break things. Ice in the south, snow in the north, Arctic cold everywhere, arriving exactly when we're least able to defend against it. And that's where this gets interesting. Because once you see the pattern, once you understand how these 3 fronts reinforce each other, you start asking questions that sound almost paranoid. But we'll get there. First, you need to see what's actually happening on the ground. You need to see the 3-front siege. Most people think extreme weather is about one thing being really, really bad. A hurricane with sustained winds of 150 miles per hour, a tornado rated EF5, a blizzard that drops 4 feet of snow in 6 hours. Our brains are wired for superlatives. We want to know which number is the biggest so we can measure the threat and feel like we understand it. Fern doesn't work that way. Fern isn't extreme in one dimension. It's destabilizing in 3 mutually reinforcing ways. And the interaction between those 3 fronts is what turns this from a bad storm into a civilizational stress test. Let's start in the south, where the nightmare is already fully operational. The Southern Ice Corridor, stretching from eastern Texas through Arkansas, Tennessee, Mississippi, Louisiana, all the way to the Carolinas, is currently being coated in somewhere between 0.8 and 1.1 inches of ice. And I need you to understand why that number, which sounds almost modest, is functionally catastrophic. Ice accumulation is not linear. The damage doesn't scale in a nice, predictable way where half an inch is half as bad as 1 inch. It's exponential. The structural load on a power line or a tree branch increases with the cube of the ice thickness. Double the ice, and you're not doubling the weight. You're multiplying it by 8. That's not weather trivia. That's physics. And physics doesn't negotiate. When you get to 1 inch of ice, you're in a different category of physical reality. Tree branches that have survived every storm for 30 years are now holding the equivalent of a small car. Power lines designed to handle wind and snow and reasonable amounts of ice are suddenly trying to support a load they were never, ever engineered for. And here's the kicker. The thing that makes this whole situation spiral out of control faster than utilities can respond. It's not just the ice. It's the ice plus the wind plus the vegetation. Every tree in the south is now a loaded weapon. The ice builds up on the branches. The wind starts gusting at 20 or 30 miles per hour, which isn't even that strong by storm standards, but it's enough to start those branches swaying. And when a branch coated in 1 inch of ice sways and then snaps, it doesn't just fall. It falls with momentum, with mass, with the kind of kinetic energy that tears through power lines like they're made of thread. And each downed line cascades into another failure, and another, until entire substations go offline and the utilities aren't dealing with outages anymore. They're dealing with grid collapse. This is the thing nobody wants to say out loud because it sounds too frightening, but I'm going to say it anyway. Utilities plan for outages. They have crews on standby. They have protocols. They have mutual aid agreements with neighboring states. What they do not plan for is simultaneous, widespread structural failure of the primary distribution network across 6 states at once. There's no protocol for that. There's no fleet of trucks big enough for that. There's just damage assessment and triage and the grim calculus of deciding which neighborhoods get power back first and which ones are going to be dark for a week. Now, shift your attention north. While the South is being encased in ice, New England and the Mid-Atlantic are being buried under snow. But this isn't normal snow. This is the kind of snowfall that makes veteran meteorologists start using words like deformation band and mesoscale banding, which are just technical ways of saying the atmosphere is organizing itself into tight, ferocious corridors of precipitation that dump unbelievable amounts of snow in very specific locations. Deformation bands are notoriously difficult to predict because they operate below the resolution of most weather models. The models know a deformation band is going to form somewhere. They just can't tell you exactly where until it's already happening. And once it sets up and stalls over your city, you're not getting 6 inches an hour. You're getting 2 to 3 inches an hour for 6, 8, 10 hours straight. That's how you get blowout totals. The kind of snowfall amounts that make the forecast look conservative in hindsight. And here's the cruel irony of this particular snow event. It's dry snow. Light, fluffy, picturesque snow that looks absolutely beautiful until you realize what it means for transportation. Wet, heavy snow is harder to move, but it compacts. It settles. Dry snow doesn't settle. It drifts. It blows across highways and piles up in places you didn't even know could accumulate snow. It makes every road a wind tunnel experiment. And because it's so light, it's almost impossible to plow efficiently. The plows just blow it around. You need multiple passes to clear a single lane, and by the time you've made your second pass, the first lane is already drifting shut again. So while the South is losing power, the North is losing mobility. Interstate highways are shutting down section by section. Airports are closing. Rail lines are buried. And this is all happening before the third front arrives. The Arctic follow-through. The cold. This is what turns Fern from a major winter storm into a potential mass casualty event. Cold air doesn't care about your preparedness plans. It doesn't care that you have blankets and canned food and a battery-powered radio. It cares about thermodynamics. And thermodynamics says that when you put a human body in a 10 below zero environment with no external heat source, that body will stop functioning within hours, not days. The post-storm cold is more dangerous than the cold during precipitation, because during the storm, you still have options. You can still drive somewhere if you absolutely have to. Emergency services can still mostly function. But after the storm, after the ice has coated everything and the snow has blocked everything and the power has failed everywhere, the cold becomes a multiplier. It takes every existing problem and makes it exponentially worse. Your house loses heat faster. Your car won't start. Your phone battery drains in minutes instead of hours. Water pipes freeze and burst, which means even if the power comes back, you might not have running water. And the people who need help the most, the elderly, the sick, the very young, are the ones with the least ability to generate their own heat or move to safety. Here's the sequence that should terrify you. Ice arrives first and takes down the grid. Snow arrives second and makes the grid impossible to repair. Cold arrives third, exactly when you need power the most, and stays for days. It's not overlap. It's a coordinated strike, a 1-2-3 punch that feels almost designed to maximize damage. And that word, designed, is where things start to get uncomfortable. Because the more you look at the timing, the more you look at how perfectly these three systems are aligning, the more you start to wonder if there's something underneath the surface that we're not seeing. Something about how the models behaved right before this storm locked in. Something that's making forecasters nervous in a way they're not used to being nervous. But before we go there, you need to understand what the models actually did. You need to see the anomalies that are keeping meteorologists awake at night. There's a quiet unease spreading through the meteorological community right now, and it has nothing to do with the storm totals. It has to do with how the models behaved in the 72 hours before Fern became inevitable. Weather models are complicated beasts, but the basic idea is simple. You feed them current atmospheric conditions, you let them run the physics forward in time, and you get a probabilistic forecast. The more the models agree with each other, the more confident forecasters become. This is called model convergence, and it's the foundation of modern weather prediction. When the American model and the European model and the Canadian model all start showing the same solution, you know you're probably looking at reality. But sometimes models don't converge gradually. Sometimes they snap. They'll show 5 different scenarios, 4 of which are mild, and 1 of which is catastrophic. And then suddenly, within a single update cycle, all 5 scenarios collapse into the catastrophic one. That's not convergence. That's phase locking. And phase locking is what happened with Fern. The high-resolution rapid refresh model, the HRRR, which updates every hour and is supposed to be our best tool for short-term forecasting, showed something on January 22nd that made absolutely no sense. It showed a precipitation lull. Right in the middle of what should have been the most intense part of the storm, the model depicted this weird gap, this 2 to 3 hour window where nothing was falling. No rain, no snow, no ice. Just a pause. Forecasters stared at that output for hours, trying to figure out if it was real or if it was an artifact, a glitch in the model's representation of reality. Because if it was real, it meant something very strange was happening with the energy phasing. And if it was an artifact, it meant the model was struggling to resolve the storm's structure, which is arguably worse because it means we're flying blind. Energy phasing is one of those concepts that sounds like jargon, but is actually pretty intuitive once you break it down. Think of it like waves in the ocean. You can have 2 small waves that merge into one bigger wave, or you can have 2 big waves that merge into a monster wave, or you can have waves that interfere with each other and cancel out. Weather systems do the same thing. They're just waves in the atmosphere instead of waves in water. And Fern is the result of multiple energy waves, multiple disturbances in the jet stream, merging at exactly the right time and place to create something much larger than the sum of its parts. But here's where it gets tricky. The timing of that merger, the phasing, is incredibly sensitive. A 6-hour difference in when two systems come together can be the difference between a manageable snowstorm and a historical blizzard. And the models kept flip-flopping on that timing, right up until the moment they didn't. Right up until the moment they all locked onto the same solution. Then there's the secondary cyclogenesis off the Carolinas, which is just a fancy way of saying a new storm is forming off the coast, right as the primary system is moving through. This is a classic nor'easter setup, and it's notoriously difficult to predict because the handoff between the inland system and the coastal system is incredibly fragile. If the coastal storm forms too early, it steals all the energy and the inland system dies. If it forms too late, the inland system is already gone and the coastal storm fizzles. But if the timing is perfect, if the handoff happens exactly right, you get a storm that feeds on itself and explodes. Guess which one happened with Fern? The coastal system formed at exactly the right moment to take the baton from the inland system and then intensify rapidly, pulling in moisture from the Atlantic and cold air from Canada and organizing all of it into this tight, vicious circulation that's now parked over New England and refusing to move. And that 6-hour window I mentioned earlier, the one that determines whether you get a foot of snow or 2 feet of snow, it shifted. The models showed the handoff happening 6 hours later than they initially predicted, which moved the heaviest snow bands 200 miles north and turned what should have been a significant event into an overwhelming one. But here's what's really making forecasters nervous. It's not that the models got it wrong initially. Models are wrong all the time. That's why we run multiple models and compare them. It's that the models all got it wrong in the same direction, and then they all corrected in the same direction at the same time. That's not normal model behavior. That's the models encountering something in the atmosphere that they weren't parameterized to handle, something outside their training data, and then suddenly figuring it out all at once. Some meteorologists think it's because the storm is now being controlled by mesoscale features, small-scale atmospheric structures that are below the resolution of global models and only show up clearly in high-resolution regional models. And mesoscale features are, by definition, chaotic. They're sensitive to initial conditions in a way that makes prediction a nightmare. A slight shift in temperature or moisture or wind shear can completely reorganize the entire precipitation structure. So we're now in a regime where the models can tell us what's happening, but they can't tell us what's going to happen 6 hours from now with any real confidence. That's why you're seeing forecasters hedge their language, why they're saying things like, confidence is low in exact placement of heaviest snowfall bands, and nowcasting will be critical. It's code. It's their way of saying, we're watching the radar in real time, because the models can't keep up anymore. And that brings us to the question nobody wants to ask, but everybody's thinking. If the models can't predict the mesoscale features, and the mesoscale features are what's controlling the storm, then what exactly are we relying on right now? Hope? Luck? The assumption that reality will be kind? But even if we had perfect forecasts, even if we could predict every snowflake and every ice crystal, it wouldn't solve the deeper problem. Because Fern isn't just exposing the limits of weather prediction, it's exposing the limits of the infrastructure we've built our entire civilization on. And that infrastructure was designed with assumptions that Fern is currently shredding into confetti. There's a concept in engineering called silent vulnerability. It refers to weaknesses in a system that don't reveal themselves until the system is stressed beyond its design parameters. You can test a bridge with trucks all day long, and it'll hold up fine, but you'll never know if it can handle an earthquake until the earthquake happens. And by then, it's too late to reinforce it. The American power grid is riddled with silent vulnerabilities, and Fern is stress testing every single one of them simultaneously. The Mississippi Delta is uniquely exposed in ways that most people don't think about until the lights go out. The infrastructure is old, not old in a charming vintage way. Old in a, this transformer was installed in 1978 and was supposed to be replaced in 2005 way. Old in a, the utility has been deferring maintenance for decades because regulators don't reward investment in reliability way. Then there's the geography. Rural areas mean long line runs. A single distribution line might serve 20 or 30 customers spread out over 15 miles, which sounds fine until you realize that one tree falling anywhere along that 15-mile stretch takes out power for everyone. And when you're dealing with 1 inch of ice and thousands of trees, you're not talking about one failure. You're talking about hundreds of failures happening simultaneously across a network that was already held together with duct tape and prayers. Vegetation density makes it worse. The South has trees everywhere. Big trees, old trees, trees with massive canopies that collect ice like satellite dishes. And when those trees come down, they don't just break power lines. They destroy them. They tear the lines completely off the poles. They snap the poles themselves. They take out entire sections of the grid that will require not repair, but complete reconstruction. And here's the thing about ice damage that makes it so much worse than wind damage, or even snow damage. Wind breaks things, but the pieces are still there. You can reattach a line that's been blown down. Snow weighs things down, but it melts. Give it a few days, and the problem solves itself. Ice doesn't melt when it's 10 below zero. Ice stays. And ice doesn't just break components, it shatters them. Insulators crack, transformers rupture, hardware freezes and fractures. You can't fix that quickly. You have to replace it. And replacement parts are in warehouses 3 states away, and the trucks carrying those parts can't get through because the roads are impassable. So let's walk through what happens. Let's trace the sequence of the deadly trap that's closing around millions of people right now. First, ice accumulates. This is already happening. Lines are sagging, branches are cracking. The sound of things breaking is becoming the background noise of the night. Second, the grid collapses. Not fails, collapses. Entire counties go dark at once as substations are overwhelmed and trip offline. Backup systems engage, realize they're overloaded, and shut down to protect themselves from damage. This is the grid doing what it's designed to do, which is preserve itself rather than try to operate in a failed state. But the result is the same: no power. Third, roads become inaccessible. The ice that took down the grid also took down the trees, and those trees are now blocking every major road and most of the minor ones. Emergency crews can't get to the damaged infrastructure because they can't get past the debris field. And even if they could, what are they supposed to do? They can't work on downed lines when those lines are buried under fallen trees and coated in ice and still potentially energized. Fourth, Arctic cold arrives. This is the part where the trap springs shut. Because now, you have millions of people in homes with no heat, no light, no way to cook food, no way to charge their phones, and the temperature is dropping below zero. Not the wind chill, the actual air temperature. And it's going to stay there for 3 days. Emergency response slows exactly when demand spikes. Fire departments get called to house fires from people trying to heat their homes with ovens and grills. Hospitals fill up with hypothermia cases and carbon monoxide poisoning from generators running in garages. Shelters open, but people can't get to them because they can't drive on the iced-over roads. And even if they could, the shelters are losing power too. This has happened before. Not at this scale, but it's happened. The ice storm of 1998 in Quebec. The ice storm of 2009 in Kentucky. The Texas freeze of 2021. Every single time, people died. Not because they didn't know it was dangerous. Not because they weren't warned. Because the infrastructure failed and there was no backup plan that could operate at the scale of the failure. Fern is not a weather problem. Fern is a time-to-failure problem. How long can you survive without power when it's 10 below zero? How long can your local hospital run on generators? How long can emergency services operate when they can't refuel their vehicles? How long before the supply chain for food and medicine breaks down because the trucks can't get through? These aren't hypothetical questions. These are questions being asked right now in emergency operations centers across 10 states, and the answers are not comforting. But here's where we need to be very, very careful. Because when systems fail this cleanly, when the sequence of events unfolds this perfectly, people start looking for patterns. They start asking whether it's coincidence or something deeper. They start wondering if maybe, just maybe, this wasn't entirely natural. And that's when the speculation begins. Let me be very clear about something before we go any further. What I'm about to discuss is speculation. It is not fact. It is not proven. It is not something you should repeat as truth. But it is something worth understanding, because the existence of these theories tells us something important about how humans process uncertainty and crisis. Alternative narratives always emerge during disasters. Always. It's a feature of human cognition, not a bug. When something terrible happens and the official explanation feels insufficient or unsatisfying, our brains start looking for other explanations. Sometimes those explanations are correct. Sometimes they're wildly wrong, and sometimes they're unfalsifiable, which makes them intellectually useless, but emotionally compelling. The grid stress test theory has been circulating in certain corners of the internet for about 48 hours now, and it goes something like this. Fern arrived at a suspiciously convenient time for anyone who wanted to see how the American power grid would respond to a combined ice-snow-cold assault. There were infrastructure reports published just weeks before this storm, highlighting vulnerabilities in the southern grid. There were policy discussions about grid modernization and resilience funding. And then, almost as if on cue, nature provided the exact scenario those reports warned about. The timing raised eyebrows. I'm not saying it should have. I'm saying it did. Because when you're scared and cold and the lights are out, your brain starts connecting dots, whether or not those dots form a coherent picture. Let me state this as clearly as possible. There is no evidence of intent. There is no evidence that anyone or anything deliberately caused or steered the storm to test infrastructure. Weather is chaos. It doesn't need help being destructive. But the lack of evidence doesn't stop people from asking the question, and the question itself is revealing. Then there's the phase locking discussion, which is a little more technical, but equally unsettling to people who understand what it implies. The Arctic air mass that's following Fern south is unusually deep, unusually cold, and unusually stable. It's not just cold air spilling out of Canada for a few days. It's a semi-permanent displacement of the polar vortex, a reorganization of the entire northern hemisphere circulation pattern that could last for weeks. What's actually unusual is not that this is happening. Polar vortex disruptions happen. They're a known phenomenon. What's unusual is how suddenly the models agreed on it. For 2 weeks, the long-range models showed a variety of outcomes. Some cold, some mild, some in between. And then, within a 72-hour window, they all shifted to the same outcome: extreme and sustained cold. No more disagreement. No more uncertainty. Just consensus. To some people, that feels uncanny. It feels like the atmosphere suddenly made a decision. And while meteorologists will tell you that's just the models resolving a previously uncertain pattern, there's a part of the human brain that rejects that explanation because it sounds too neat. It sounds like something clicked into place. And things don't just click into place in chaotic systems unless something made them click. The Arctic Gate hypothesis takes this even further into speculation territory. It suggests that we're not looking at a temporary pattern shift, but a permanent regime change. The idea is that the polar vortex has been destabilized to the point where it can no longer contain Arctic air the way it used to, and we're entering a new climate state where these extreme cold outbreaks become the norm rather than the exception. Some versions of this theory invoke climate change. Some invoke solar cycles. Some invoke feedback loops in the jet stream that we don't fully understand. All of them share a common thread of fear about losing control of something we thought was stable. And here's the uncomfortable truth. We don't know if that fear is justified or not. The science on polar vortex behavior is still evolving. We know it's changing. We know the changes are connected to Arctic warming. We know the jet stream is getting wavier. What we don't know is whether those changes have crossed a threshold that makes them irreversible or self-reinforcing. And not knowing is terrifying. Cognitive pattern seeking under uncertainty is a survival mechanism. Our ancestors who saw patterns in the rustling grass and assumed a predator were more likely to survive than the ones who assumed it was just wind. We're wired to see agency, to see intention, to see design, because that's how you stay alive in a dangerous world. But in the modern era, that same wiring makes us vulnerable to seeing conspiracies and control where there's only chaos and chance. So let me separate things very clearly for you. What's proven? Fern is a real storm causing real damage. The models struggled to predict certain aspects of it. The infrastructure is failing in predictable ways given the magnitude of the stress. The Arctic cold is real and dangerous. What's speculative? That the timing of this storm is anything other than coincidence. That the model behavior indicates anything unusual about the atmosphere beyond normal chaotic sensitivity. That we're entering a permanent new climate regime rather than experiencing a temporary pattern shift. What's emotionally explanatory but scientifically unfounded? That someone or something wanted this to happen. That there's a hidden layer of causation we're not seeing. That this is a test or a message or a warning from forces beyond our understanding. I'm not mocking those theories. I'm contextualizing them. Because the impulse to find meaning in chaos is deeply human, and it deserves respect even when the theories themselves don't hold up to scrutiny. But uncertainty does not equal conspiracy. Unknown does not equal unknowable. And the fact that something seems too perfectly destructive to be natural doesn't mean it isn't natural. Nature is very, very good at destruction. It's had 4 billion years of practice. And Fern isn't the only system right now being pushed past its design limits. Because while we've been focused on the atmosphere, something else has been escalating. Something in space. Something that mirrors Fern's themes in ways that are genuinely unsettling. While the United States is being paralyzed by ice and snow and cold, the sun is going through its own version of a superstorm season. And the timing, once again, is raising questions that make people uncomfortable. We are currently in solar cycle 25, and it is turning out to be significantly more active than scientists initially predicted. The sun operates on an 11-year cycle of magnetic activity, oscillating between solar minimum, when it's relatively quiet, and solar maximum, when it's covered in sunspots, and erupting with flares and coronal mass ejections. We're approaching the peak of cycle 25 right now, in early 2026, and the sun is not behaving the way the models said it would. Sound familiar? The predictions made just a few years ago suggested this would be a relatively weak solar maximum, comparable to the last cycle. Instead, we're seeing sunspot numbers and flare activity that rival some of the strongest cycles on record. The sun is more active, more volatile, more unpredictable than the models anticipated. And just like with Fern, the models didn't see it coming until it was already happening. Solar flares and geomagnetic storms are increasing in frequency and intensity. These aren't abstract events happening millions of miles away, interesting only to astrophysicists and satellite engineers. These are electromagnetic disturbances that interact directly with Earth's magnetic field and can cause real, physical damage to satellites, power grids, and communication systems. The kind of damage that cascades. The kind of damage that compounds. The kind of damage that doesn't care about your emergency response plans because it happens faster than you can respond. We've been lucky so far. Most of the big flares have missed us or happened when Earth wasn't in the line of fire. The geometry of space is on our side most of the time. The sun erupts in all directions, and Earth is a tiny target. But luck is not a strategy, and our infrastructure is just as vulnerable to space weather as it is to terrestrial weather. Maybe more vulnerable, because at least with terrestrial weather, we have warnings. We have radar. We have satellites watching the clouds form. With space weather, our warning time is measured in minutes to hours, not days. Let me explain geomagnetic storms in the simplest possible terms, because this is important, and most people don't understand the mechanism. The sun occasionally hurls billions of tons of charged particles into space at speeds approaching several million miles per hour. These coronal mass ejections, CMEs, are like tsunamis in the solar wind. When those particles hit Earth's magnetic field, they cause it to fluctuate wildly, compressing and stretching and vibrating like a bell that's been struck. Those fluctuations induce electrical currents in anything conductive: power lines, pipelines, railroad tracks. Even the ground itself becomes a conductor. And when you induce currents in a power grid that's already operating near capacity, already stressed by normal demand, bad things happen very quickly. Transformers overheat because they're suddenly carrying loads they weren't designed for. Circuit breakers trip trying to protect the system. Voltage regulators fail. And in extreme cases, the entire grid can cascade into failure, section by section, substation by substation, like dominoes falling in slow motion. This is not theoretical. This is not a computer simulation of what might happen. This happened. The Carrington event of 1859 was a solar storm so powerful that it induced currents strong enough to set telegraph equipment on fire. Operators got shocked touching their equipment. Papers on desks ignited spontaneously from sparks jumping off the wires. Auroras, normally confined to the polar regions, were visible as far south as the Caribbean. People in the Rocky Mountains woke up at midnight thinking it was dawn because the sky was so bright. And that was in an era when our most advanced electrical infrastructure was telegraph wires, simple copper lines carrying simple signals. Imagine what that same storm would do to the modern power grid, with its high voltage transmission lines carrying hundreds of thousands of volts across thousands of miles. Imagine what it would do to our satellites, our GPS systems, our communication networks, our financial infrastructure that relies on precise timing signals from space to process billions of transactions per second. We've had near misses in the modern era, events that should terrify us more than they seem to. A Carrington-class storm missed Earth by about 9 days in July 2012. The coronal mass ejection tore through Earth's orbit, right through the space where our planet had been just over a week earlier. If the timing had been different, if Earth had been in that spot when the CME arrived, estimates suggest it could have caused $2 trillion in damage and taken 4 to 10 years to fully recover from. And that's assuming we could recover at all, because some of the components in our grid, particularly the large high-voltage transformers that step power up and down between transmission and distribution voltages, have lead times measured in years. Not months. Years. You can't just order a replacement from a supplier and have it delivered next week. They're custom built, each one designed for a specific substation with specific requirements. There are only a handful of facilities in the world that can manufacture them. And if a Carrington-class event took out hundreds or thousands of these transformers simultaneously across multiple continents, we'd be looking at a recovery timeline that extends beyond anything modern civilization has ever dealt with. So here's the parallel to Fern, and this is where the pattern becomes impossible to ignore. We have an infrastructure built for average conditions being stressed by extreme events. We have models that struggle to predict the most dangerous scenarios until those scenarios are already unfolding. We have cascading failures that compound faster than we can respond. We have a system that's functionally irreplaceable on short timescales, where short means anything less than several years. And we have a growing sense that maybe, just maybe, we've been lucky for far too long, and that luck is a finite resource. The solar cycle doesn't care about our level of preparedness. It doesn't wait for us to harden our infrastructure or build redundancy into our systems. It operates on its own timeline, driven by magnetic dynamos deep inside the sun that we barely understand. And right now, that timeline is bringing us towards solar maximum with more activity than predicted, more volatility than expected, more potential for a catastrophic event than the model suggested was likely. Now let me ask you the question that keeps risk analysts awake at night, staring at the ceiling and running scenarios in their heads. What happens if a Carrington-class solar storm hits during a Fern-scale terrestrial disaster? What happens if the grid is already down from ice damage, already operating on emergency backup systems, already pushed to its absolute limits? When the geomagnetic storm arrives and fries the transformers that were supposed to bring it back online? What happens if we lose satellite communications and GPS during a blizzard when emergency services are already overwhelmed and can't navigate without those systems? What happens when the backup communications fail because they rely on infrastructure that just got fried by induced currents? What happens when the supply chain for replacement parts breaks down because the trucks can't get through and the logistics networks can't function without GPS and the warehouses can't process orders without power? I'm not predicting this. I want to be very clear about that. I'm not saying this is likely or imminent or something you should lose sleep over tonight. I'm saying it's possible. And the fact that it's possible, the fact that we can trace a plausible chain of events from here to civilizational collapse, means we should be thinking about it, preparing for it, building systems that can withstand it. Because the assumption that disasters happen one at a time, that we'll always have a grace period to recover before the next one hits, is an assumption our infrastructure was built on. And assumptions break. They break when stressed. They break when tested. They break when reality decides to ignore the rules we thought were universal. The broader pattern here, the thing that connects Fern and solar storms and infrastructure vulnerability and model failure, is about thresholds. Systems don't degrade linearly. They don't give you a smooth, predictable curve from working fine to completely broken. Weather doesn't care about averages. Infrastructure doesn't fail gradually. Systems operate within tolerances, handling stress and strain and unexpected loads until they don't. And then they fail catastrophically, all at once, with a speed that feels almost intentional. The distance between everything is fine and nothing works can be crossed in minutes. A transformer doesn't slowly burn out over days. It overheats and fails in seconds. A power line doesn't gradually lose capacity. It either holds or it doesn't. And once the cascade starts, once the first domino falls, the speed of collapse is terrifying. Fern is teaching us that lesson in real time, showing us what happens when ice and snow and cold align perfectly to stress every weak point in our infrastructure simultaneously. The sun might teach us the same lesson eventually, with a geomagnetic storm that finds every vulnerability in our electrical and communications networks all at once. The question is whether we're willing to learn it before the exam, whether we're willing to invest in resilience before we're forced to rebuild from ruins. But that brings us to the hardest question of all, the one that sits underneath everything we've talked about, the one that challenges the entire premise of modern technological civilization. Can we even predict these thresholds? Can we see them coming with enough warning to do something about them? Or are we fundamentally limited by the nature of the systems we're trying to understand, trapped by chaos and complexity and the inherent unpredictability of nonlinear dynamics? Because if prediction has limits, if there are events we simply cannot see coming, no matter how sophisticated our models become, then our entire approach to risk management needs to change. And that change might be more uncomfortable than any storm. Here's something that's going to sound contradictory. Weather forecasting has never been better, and we're more vulnerable to surprise than we've ever been. Artificial intelligence is revolutionizing atmospheric prediction. Machine learning models trained on decades of satellite data and historical observations can now generate forecasts that rival or exceed traditional physics-based models. They're faster, they're more computationally efficient, and in some cases, they're more accurate. GraphCast, Pangu Weather, ForecastNet, these aren't science fiction. They're operational systems being used right now to predict everything from hurricanes to heat waves. So why didn't they predict Fern more accurately? Why did all these cutting-edge AI models struggle with the same phase locking and mesoscale features that the traditional models struggled with? Because better models don't remove chaos. They just push the prediction horizon a little further out before uncertainty takes over. And Fern is a reminder that there are hard limits to predictability that no amount of computing power or training data can overcome. Nonlinear systems, which is what the atmosphere is, have a property called sensitive dependence on initial conditions. You probably know this as the butterfly effect. A tiny change in the starting state of the system can lead to radically different outcomes. And the problem is, we can never measure the initial state perfectly. We can't put a thermometer on every cubic meter of the atmosphere. We can't measure wind speed at every altitude with perfect accuracy. We're always working with approximations, and those approximations compound over time until the forecast becomes meaningless. Fern is a case study in threshold behavior. For weeks, the pattern looked like it might produce a significant storm, or it might produce nothing. The system was balanced on a knife's edge, and the smallest perturbation could tip it either way. And then something tipped it. Maybe it was a temperature anomaly over the Gulf of Mexico. Maybe it was a wind shift in the stratosphere. Maybe it was something so small we'll never identify it. But once it tipped, the cascade was inevitable. The scary part is that threshold systems give you no warning. They look stable right up until the moment they aren't. And smooth trends breed false confidence. If you're watching a river slowly rise, you can prepare for a flood. But if the levee holds and holds and holds, and then suddenly breaks all at once, you don't get a chance to prepare. You just get wet. This is the fundamental problem with prediction in complex systems. We can identify the ingredients for disaster. We can say, these conditions make extreme events possible. But we can't say, this specific event will definitely happen at this specific time until it's already locked in. And by then, it's too late to do anything except respond. So what's the alternative? Preparedness over prediction. You can't forecast the exact moment a transformer will fail, but you can harden the grid so it's less likely to fail. You can't predict the exact track of a deformation band, but you can build redundancy into your transportation network so one blocked highway doesn't paralyze an entire region. You can't predict when the polar vortex will destabilize, but you can ensure that every home has access to backup heat sources and every community has warming shelters. This is where AI and weather and space, weather and infrastructure all come together. Because the lesson isn't about prediction, it's about uncertainty. It's about recognizing that no matter how good our models get, there will always be surprises. There will always be events that exceed our expectations. There will always be thresholds we don't see until we cross them. Fern didn't just hit the United States. It hit the assumptions we've been relying on. The assumption that the grid is robust. The assumption that emergency services can always get through. The assumption that disasters give us warning. The assumption that nature operates within bounds we understand. And maybe that's the real story here. Not the ice totals, or the snowfall amounts, or the temperature records. Not the model forecasts, or the infrastructure failures, or the speculation about causation. The real story is that we built a civilization on the premise that we could control our environment, or at least predict it well enough to stay ahead of it. And Fern is a reminder that control was always an illusion. Prediction was always provisional. The stability we took for granted was always temporary. The atmosphere doesn't owe us predictability. The sun doesn't owe us consistency. The climate doesn't owe us stability. And the infrastructure we've built, as impressive as it is only as reliable as the assumptions it was designed around. Those assumptions are being tested right now. Some of them are failing. And we're about to find out which ones we can rebuild and which ones we need to abandon entirely. Fern didn't just bring ice and snow and cold. It brought a question. A question we've been avoiding for decades because the answer is uncomfortable. How much of our safety is real and how much is luck? How much of our technology is actually protecting us and how much is just delaying the inevitable? I don't have the answer. Nobody does. But I know this. Every storm is a teacher. Every failure is a lesson. And the only thing more dangerous than acknowledging our vulnerability is pretending we're invincible. So as Fern continues to tear across the continent, as the ice piles up and the snow drifts and the cold settles in, maybe the smartest thing we can do is pay attention. Not just to the weather, but to what the weather is revealing about us, about our systems, about our assumptions, about the fragile scaffolding we've built our entire world on. Because the next Fern is coming. Maybe next year, maybe next decade, maybe from the sky, maybe from space, but it's coming. And when it does, the only question that will matter is whether we learned anything from this one.